minus 4AC. Okay? So then what we learned was that whatever number this gives us tells us something else about the problem. Remember, because I have like those lists of questions I want you to answer. So this was our number 6, was the discriminant. So after we know, maybe what order what form it's set up in, then we can know the direction, the shape of it, where the vertex lies, the axis of symmetry, and then the discriminant tells us how many solutions we have. Because if our discriminant turns out to say we should have no solutions, then when we're solving for it, we should have no solutions, right? So it's just that extra check that we have. So what happens when your discriminant gives you a positive number? How many solutions should you have? 2. 2 real solutions. So if your discriminant is positive, that means that you will actually have the square root of something, right? And since we have plus or minus, we will have one solution that is plus the something, and we will have one solution that is minus the something. So therefore, we get 2 solutions, okay? If your discriminant turns out to be 0, how many solutions will you have? If the discriminant is 0, you're going to have 1. So let's think about why. So if this part is 0, I now have negative b plus or minus the square root of 0 over 2a. What is the square root of 0? 0. So that doesn't matter. So when my discriminant is 0, all I'm left with is this really important part, which tells me the vertex. So when our discriminant is 0, we have one solution, and that solution is the vertex of the parabola. So you see how that's working out? Now, if my discriminant comes out to be negative 53, so now underneath here I have the square root of negative 53. How many solutions do I have? 0. Or no. No real solutions. That means because I would end up with an I value, right? And when we were graphing, we said we've got the real line and our imaginary. So since I have an I value, it's moved up. That means my parabola is somewhere in space. And the reason it has no real solutions is because solutions are equal to what? X. Solutions are only points where it crosses the x-axis. That's what solutions are. Remember, we called them solutions. What else were they called? Roots. And one more word. When y equals, these are all points when y equals 0. Zeros, okay? Solutions, roots, and zeros, all the same name for the same exact points. Okay, so yeah, we have a real parabola that's up here, a real quadratic. We could have a real quadratic that's down here. It just doesn't have a solution. It doesn't have any place where it actually crosses the x-axis. Okay. Any more questions on that? Any questions on imaginary and complex numbers? Multiplying them. What is I squared? Negative 1. What is I cubed?
Negative I, I think.
I cubed is negative I. What is I to the 4th? 1. Okay. So if I have I times I in something, and I get I squared, am I going to leave that as I squared?
No.
No. We're going to replace I squared with negative 1, and then work out the rest of the problem. Okay? Can a complex number with the number 14? Yes. Why?
So you can add 0 to 5.
Plus 0i. Okay. Can I have a complex number with 6i? Can I make this a complex number? Yeah, because I can just write 0 plus 6i. So I have my real part and I have my imaginary part. Okay? So all numbers can be written as complex numbers. Right? That's important. You'll need that too.
Isn't the formula for that a plus bi?
Yeah, it can be written as a plus bi. Just means, different numbers. Okay. So standard form of a quadratic is what? We have 3 different forms. Let's talk through the 3 different forms. The first form is standard.
Vertex and factored.
Standard, vertex, and factored. So standard is going to have an equal to 0, right? And all of your information on the other side. Vertex is basically going to be a y equals, right? It could say f of x because f of x is just another name for y. So y equals, we're going to have information A, x minus h plus k. What is the vertex? HK. The h will always be the opposite of the sign. So if I have x minus 3, my x value is what? Positive 3. Okay. K always goes with the sign. Again, as we move forward, we're going to be doing polynomials this week. Same thing. Think about it. My x and my number are grouped together on the same side of the equal sign. So for me to get an x equals to something, I have to move it over. When we change sides, we change signs. That's why we've changed this one. The k is already on the opposite side of the equal sign because y is over here on the left. So I don't have to change the sign for the k. So if I had 4x minus 3 squared plus 5, my vertex would be at 3, 5. Okay? 4 tells me it faces what direction? Is it skinny or wide?
Skinny.
Skinny, because a slope of 4 would be a much greater slope of a line, and then all I'm doing is just curving it and having it on the other side. So it's going to be skinny. And I know where my vertex lies, and it goes up. So if I wanted to sketch it, I could go 3, 5. It's going up. It's pretty skinny. I could go ahead and just kind of sketch it. My axis of symmetry is where?
3.
X equals 3. Do not write 3. If you say axis, if I ask you for axis of symmetry, do not write a number. The axis of symmetry is a line. So since it's a line, it has to have the equation of a line. Okay? So it must be x equals a number. Got it? Any other? I think that'd be it. And then factored form. Will factored form ever have a squared term? An equation in factored form? No, because we've taken out the squared, right? So a factored form might have x plus 3, x minus 5. Okay? Factored form, so it just tells me my solutions. My solutions, where does this cross? What are my solutions?
-3.
-3, 0, and 5, 0, right? Because this is where y equals 0. We're asking that question. When y equals 0, where is this graph going to go? And if y is equal to 0, that means one of the terms must equal 0. So we take each of our terms and we set them equal to 0. When I change sides, I change signs. So now I have x equals -3. So I'm saying I've got 1 point here at -3, 0, 1 point at 5, 0. What's the axis of symmetry on this one? What's the axis of symmetry?
Positive one.
Positive
or
2.
1.5. Somewhere in there.
What was the first thing you said?
1.
1. Okay. The difference between 5 and 3 is 8, right? 5 and negative 3, I have 8. So my axis of symmetry has to go smack in the middle. So I've got to go 4 from one side, 4 from the other side. So if I'm going 4 this direction and 4 this direction, I'm going to end up at x equals 1. So now what I automatically know about this, my vertex is at 1 something, right? So we're able to take where we're at and start gathering all of our information. So here we started with solutions. My axis of symmetry has to fall right in the middle of them. So we find the mean of them, the average of it. Goes right in the middle. It also, but then the axis of symmetry also tells me the x value of my vertex. So then to find the y value, I simply do what? When x equals 1, I'm going to plug it back in. So I'd have 4 times 4, so y would equal 16.
So to find the axis of symmetry, you don't add the 2 as if they were both positive or negative and take the.
Oh, that's negative.
Wait, what did you get? 16?
Negative 16. Sorry. 4 and negative 4. Okay, what were you asking, Will?
So to find the axis of symmetry, you combine them as if they were both positive, and then take the half of that, I guess, and then count from each point.
Well, so I want to find the difference,
Yeah.
and the difference it always means subtraction. So I actually am doing 5 minus a negative 3,
Okay.
which is how I ended up with 8.
Okay.
When we graph it out, sometimes you can just count it and be like, well, to get from here to there, I need to go 3 until I get to the origin, and then I need to go 5 more to get to this one, so I have 8 between there. If I was at positive 3 and 5, the difference between them would be 5 minus 3, so that would only be 2.
So then that would be 2.
So if I have a difference between 2 points of 2, then the middle is 1 away from each of them. So then that would be at x equals 4. We're finding the difference between them, and then we have to split it in half.
Okay.
So we take the difference, we divide by 2, so that we can split it right in the middle. You know, but that number, so in this way, 8 was 4, well, it doesn't give me a 4, it just means 4 from those points. So then either you're going to subtract 4 from 5, or you're going to add 4 to negative 3. Again, feel free to sketch, you know, so that you can figure out those things. Does that make sense?
Yeah.
So once you have your axis of symmetry, you automatically have your vertex x value. Once you have your vertex x value, you can plug it back in and get your vertex y value. Right? And then any of our coefficient numbers that are added simply tell us the direction and the shape of the parabola. Okay. If you've not done your review, your chapter review, please do it before you take your test. If you've not done the online quizzes practice, let me know. I'll open it back up. Please take that before you take your test. So a quadratic does what? It bends lines, so we're always going to have the shape of a what? Parabola. Okay. Any more questions over last week's work? Any of the radical review? Because we're going to move with the radicals and move on up to exponents. We're going to learn how to undo. Now we're going to learn how to go back and forth. It's that seesaw. Okay? So we were looking at lots of radicals. Square root of 16. So we had our index number, right? It tells us how many we need of the same. So we need 2. I would need to find 2 of the same number. In this case, I would say 4 times 4. I need 2. I have 2. It would escape as a 4. And we can work with our radicals. So the opposite of roots are exponents. So just like multiplication, division, addition, subtraction, we go back and forth. So now we have some rules for radicals. We learned those. Now we're going to go back and learn their opposites, the exponents. So again, we're just doing that whole, tipsy back and forth. If we can do it one way, how can we undo it the other way? Okay. So exponent rules. This is available for you to print. It is on the classroom handouts. Or I'm going to show you a couple different ones. So again, up to you if you want to have them in your notebook. But this one is available. It's a nice little cheat sheet. It has all of the rules that we're going to go over it together in one nice little place. I also have this integer exponent properties sheets. It's 4 sheets, and you can print that out and put it in your notebook as well. It is already filled in with the answers. So this is not, again, not something that I'm asking you to like do for homework, whatever. It's available to have as a note, to have as extras if you'd like to have it. And it's called the integer exponent properties, and it is also under the classroom handouts. And we're going to walk through all these different things. So this 4-part sheet is the explanation for all of these, of how we get through the exponent rules, okay? So there's 4 different sheets on this. All right, so chapter 6, as we move forward for chapter 6, we just learned how to deal with quadratics. And along with quadratics, we learned about some radicals and some complex numbers along with it. And so now we're going to move into chapter 6, which is polynomials. So we started with linear, right? Linear equations were mx plus b. We actually have an exponent, we just don't see it, right? It's the exponent of 1. Then we moved up to quadratics, where we've got x squared terms, right? So now when we start moving up, we're going to call those polynomials, okay? Remember when we talked about a monomial might just be 3x. A binomial would be 3x plus 2. It has bi, it has 2 terms. A trinomial has 3 terms. Polynomial just means it's multiple. Poly means multiple. So we're just looking at things that have more than 1 term. Okay, so we're going to look at solving them, how we get there, how to look at their graphs and figure out their graphs in the same way that we have figured out linear equations and we figured out quadratics. So my question would be, was there similarity between the linear equations and the quadratic equations of how we looked at them and figured out what direction and what shape and things like that? Was there similarity there? Yeah. Do you think there will still be those same similarities as we move forward?
Yeah.
Yes. It's great. Again, it's not new, okay? So, again, I just said before we actually look at the quadratics, we're going to see how to get there, okay? That's what I just talked about. Okay, so exponents. We were dealing with roots, so now we're going to have a little mini lesson on exponents. Exponents are the little number, a superscript over it. It just tells us how many we have of something in the multiplication form, whereas a coefficient tells us how many we have when we add things together. So if I'm doing x plus x plus x and I'm adding them, then it gets a coefficient on the front, right? If I do x times x and I'm multiplying them, it gets an exponent up top, okay? This tells us it's multiplication, the coefficient tells us it's addition. Okay, so when we have them, you just know that x times x is x squared. We've just always done that, okay? If I had x squared times x squared, it would be x to the 4th, okay? Officially, there's a rule that says when we multiply numbers that have the same base, then all we do is add the exponents, which is what we've been doing. We just haven't formally said that. We haven't said, oh, 5 plus 1 is 6. We're not thinking, oh, this is an m plus n. So that's the rule initially for our exponents. Okay. So we're real familiar with multiplying with the same bases. What happens when we start raising them to a power? So if I have x squared and I raise that to the 3rd. So now I have x squared cubed. Okay? So the rule for that is instead of adding, we we're actually gonna take the two exponents and multiply them together instead. So any exponent raised to another exponent gets multiplied together. And let's think about why that is. So I have on this one, m cubed is now squared. So what it really means is n cubed times n cubed. Well, from my rule that I just said, if I have the same base, then I add the exponents. So this would be 3 plus 3 would be 6. Well, 6 also comes from 2 times 3. So we're just getting it a different way without actually having to write out everything that we mean. And the same way here, so we've got x squared to the 4th really means x squared times x squared times x squared times x squared. According to our multiplication rule, when they all have the same base, we add the exponents together. So I ended up with 8. It's a lot faster for me to just say 2 times 4 is 8 than it is to multiply this out. Because if I were to have x squared to the 32nd, do I want to write this out 32 times and add 32 2's together? No, I can just say it's x to the 64th. We're just going to multiply them. So anything that's raised to a power will multiply. Questions? No one? Okay. So distributive, when we've had regular numbers and we have those parentheses, we always distribute, right? Everyone hates our negative distribution, right? Because we lose it along the way. But if I were to have negative 3 times x plus 6, I would take my negative 3 and I would multiply it and distribute it all the way through and get negative 3x minus 18. In the same way, we can take exponents that are raised and we can distribute them. So if I've got m times x to the a, my b here deals with my entire mx to the a. So my b gets distributed to the first term in m to the b, and then it gets distributed to the x term, which then makes a power to the power. So we multiply those together. Okay. Is that confusing, Joshua?
A little bit.
Okay, I'm going to put real numbers in there. Okay, so if I had 3x squared to the 4th, okay, mx to the a to the b, okay, 3x squared to the 4th. This 4 gets distributed to both, so I'm going to break it up. And I'm going to say what I really have is 3 to the 4th times x squared to the 4th. Okay, step 1, we're going to distribute it out. Step 2, we then reduce everything that we know according to the other rules. So 3 to the 4th is going to be 81. So I had 81 here. Now x squared to the 4th, we just learned, is a power to a power. So I could write out x squared times x squared times x squared times x squared. Instead, I'm just going to say, I know that any power raised to a power, I multiply. So now I have x to the what? X to the 8. Okay. Does that make more sense with numbers? Okay. On the one that's fine, on the bottom, a to the b, we're just going to put the m with each one, right? So we have a to the m times b to the m. So we can divide that out as long as we have all multiplication. Now this does not work if there is an addition or subtraction sign in here. Do not do that. Okay, these are only multiplication and division rules for our exponents. Right, so I've got a couple of examples there at the bottom. So on the bottom one I had 5, I broke it out. So I changed it to 5 squared, then our x cubed squared, and our w cubed squared. So the first thing that we did here is distribute out our squared term. And then we're going to simplify. 5 squared is 25. X cubed squared, we multiply. 3 times 2 is 6. And on this one, I've got cubed squared again, so I'd have 6. So that's how I got my 6's across the board. Right? Division property. Okay, let's think through division. If I told you 10 over 5, you would tell me 2, right? 3/5, right? Because what I really did is I broke up my factors and I said 15 is 3 times 5, 25 is 5 times 5. Any number divided by itself is equal to the number 1. So it cancels. Again, I want you to always remember it's canceling as a 1. It's not canceling as 0. It's canceling as a 1, but 1 doesn't change anything. It's the identity when we come to multiplication, so we don't have to think about it. So anytime we have something multiplied and it's divided by itself, it equals 1. So in effect, we just kind of get rid of it. So if I have y times y over y, I can cancel one of the ones in the top with one of the ones in the bottom because this grouping equals the number 1. Okay? So effectively what I have done is I had 2 on top and I had 1 on bottom, so I subtracted 1 from 2. 2 minus 1 leaves me with 1. Because for every one that I have on the bottom that matches a top, we're going to get rid of it. So the way that we write that is if I have an exponent on the top and an exponent on the bottom, I can subtract them to end up with what I've got. So if I have x5 over x squared, this is what it looks like really. I can cancel out the 2 groups because they both equal the number 1, and all I'm left with is 3 x's on the top. Correct? It's also the same as 5 minus 2 gives me 3. Questions on that one? So on this bottom one, we had x cubed, y to the 11th, x, y to the 6th. I could write it out completely like this. Break all of the parts down into their factors, their lowest factors, and then just go ahead and cancel. Right? Whenever I did that, I ended up with 2 x's and 5 y's. I also get 2 x's by doing 3 minus 1 and 11. Oh, that should be a 6. 11 minus 6. It gives me a 5. So these are the shortcuts for what we're actually doing. These are the shortcut equations. Okay? So if we can multiply and we can distribute, can we distribute and divide? Yes, we can combine all of these and do them all at the same time or in different steps. So that first one, we have AB to the 5th and then AB to the 3rd. So the first step on this one is what? What's distribute. So we're going to use our distribute rule for our first step, and that gets us a to the 5th, b to the 5th over a to the 3rd, b to the 3rd. Okay? And so then I know that I have the same base. You can only do the ones with the same base. So with my a's, I can do 5 minus 3 gives me 2. On the b's, 5 minus 3 gives me 2. Okay, so that's one way to do it. Or because we could look at this AB as maybe an x, right? So if I'm substituting, I could say what I really have is x to the 5th over x to the 3rd, which would leave me 5 minus 3 x squared. And oh wait, I called x AB, so I'm just replacing that. So we can use substitution. We can look at it as a whole group like this. We can look at them as the whole groups, or we can break it out in division. Both answers end up exactly the same. No matter which way you choose to do it, you'll get the exact same answer. You should always get the same answer. Okay? So negative exponents. Our number 1 math rule that involves an equal sign, okay? If I go from one side to the next, I have to do what? Change signs, okay? So that flip always requires you to change a sign, right? That's the rule. If we change sides, we have to change signs. That same rule applies for exponents. If we change sides from top to bottom, we have to change signs. So if I have a value that has a negative exponent, I can change the side and it will change the sign, okay? You will never ever leave a negative exponent in a solution. It must always be rationalized out to a positive number, okay? So just know negative exponents are a no-no. We don't ever leave them. So for this first example, I've got x to the negative 2. I can't leave it as x to the negative 2. So currently, x to the negative 2 really is x to the negative 2 over 1. Remember, every number can actually be written as a fraction. If I have the number 3, I can really write it as 3 over 1. So it's really over 1, and so I've got a negative up here. I want to change the sign, so I have to change sides. I'm going to flip my fraction over. So it's going to be 1 over x squared. In the same way, if my negative exponent starts in the bottom, I can't leave it negative. I need it positive. So I've got to change sides. It's got to go from the bottom to the top. Now, so I said just like equations, we change signs. So on this one, we're going to use our rule that we just learned. Y to the third over y to the 7. What is our division rule that we knew? Y 3 minus 7, right? So this would give me y to the negative 4th. Can I leave it as y to the negative 4th? No, I have to put it on the bottom, so I've got y to the 4th on the bottom. And if we see, when we actually write out our factors and we cancel out what we can, what we really ended up with was y to the 4th. But our division property worked, our negative exponent property worked, and we end up with the same answer both ways, right? Okay, so here's a couple of extra examples. So for this first one, I've got x to the 4th, x to the 5th, y to the negative 2nd over x to the 6th y. The first thing that we're going to do is we're going to start at the beginning. We're going to combine what we can. Remember, we combine like terms, which gives me that x to the 9th. 4 plus 5 is 9. The second problem is I have a negative here. So I'm going to put it where it's supposed to be. If it's on the top, it now has to go to the bottom. So now I have it down here. Now I get to go back to the beginning. I can combine like terms again. So I have x to the 9th on the top, x6 on the bottom, and my y plus y squared gave me y cubed. Okay, so now that I have it fully simplified, I can use my division rules. If I have 9 on top and 6 on the bottom, I'm left with 9 minus 6 is 3. 3 on the top, and y cubed on the bottom. So we just take each one of our rules and work through step by step. Let's look at this one. 14, x to the 4th, y to the 3rd, and then 21, x 12, y to the 4th, z to the 5th. Okay? So I wrote out the factors of 14 and 21, just like I would for a regular simplifying any sort of fraction, right? And for my own sanity, because I was showing it with canceling, I chose numbers that I already had. So if I've got 2 times 7 for my 14, I left my x and my y. On the bottom, I've got 3 times 7. Well, on top, I have x to the 4th. So I need an x to the 4th group on the bottom. So all I did was break up my 12 into 4 and 8. Could I break up this 12 into anything that I wanted? Yeah, because my rule is all I'm doing is adding those 2 exponents. And I can get 12 with 1 plus 11, 2 plus 10. Like, I can pick any exponents that I want in there. I chose 4 because I know I have a 4 on the top. And because in this case I was showing how to cancel. Okay, I did the same thing for the y. I have a 3 on the top, so I broke it up, and if I have 4 y's, I mean I have a 3 and a 1. We can cancel out all the things that are exactly the same, and we look at what we've got left. If we used our division rules, let's see what that looks like. Okay, so we would start with 14 over 21, which is going to give us 2/3, right, if I take a 7 out. And if I look at my x's, what I really have is x what? 4 minus 12. 4 minus 12. My y is 3 minus 4. And my z stays on the bottom. Right? Or I don't have any z on top, so it's actually z0 minus 5. Okay? So then I have 2/3 x to the negative 8, y to the negative 1, z to the negative 5. Right? All of these are negative, so can they stay up top? Nope, we'd put them on the bottom, so that gives us 2/3 x8 y z to the 5th. Okay, we ended up with the same answer. We just used our subtraction of our quotient rules. Okay, so if you want to draw it out and sketch it, if you want to use your rules, if you want to use certain rules first, other ones, again, it's all personal preference. They all still work, no matter what order you put them in. Okay, zero property. This is important, especially as next semester whenever we get into exponential equations and logarithms. Okay, any number to the power of 0 is the number 1. You need to memorize that. Okay, and that's just because we're looking for, we're looking for groups of something, but I don't have any groups of it, so does it change anything? No, because I don't really have anything. And what's the number in math that doesn't change anything? It's the number 1. Okay, so any number raised to the power of 0 will always be the number 1. So we can see that it works because if I had x cubed times x to the 0, my rule says that I have to add my exponents, right? So 3 plus 0 gives me 3. So I ended up with the identity. So if I ended up with the identity, by definition of the identity, this x to the 0 must be the identity term. And the identity term for multiplication is the number 1. So we've just proven that x to the 0, here's a proof for you, x to the 0 is 1. Okay? In the same way, if we were subtracting W5 over W0, I know my rule says that I have to subtract my exponents. 5 minus 0 is 5. So again, I ended up with the identity. So how do I get a number divided, what can I divide it by to get itself? The number 1. So these are the proofs of why x to the 0 is 1. Okay? So on the one on top, the first step here would be to distribute. You've got a power raised to the power, so you're going to distribute that. The second would be that you're going to deal with any negative exponents and move them up, and then we're going to combine like terms. Once we have everything kind of combined and nice, then we can use our division and start canceling out, and then take care of any more negatives that we have. So we just go through each of our rules to simplify from something that has a lot to something that has little. Okay, so here's an example of how we might use it. Okay, the radius of the sun is about 109 times, there's an important word there, times as great as the Earth's radius. How many times as great as Earth's volume? is the sun's volume. Okay, they give you something like this, and you're like, a lot of information in one word problem. How do I start breaking it down? Okay, so the first thing that I need to know, what do they ask me? How many times as great as the Earth's volume is? So there's my is always means equals. So I'm going to write my equal sign down. I'm going to look back. What was it before? How many times? So how many times as great as the Earth's volume? So I'm going to say Earth's volume is the sun's volume. Okay, so now I've taken my word problem and I've written it into an equation. How many times of the Earth's volume is the sun's volume? Okay, well, what do I know? Volume of a sphere is 4/3 pi r cubed. If you've been in geometry yet. Okay, so now I just get to plug that information in. Okay. So I have a volume if my Earth's radius is r. So for Earth I would have my 4/3 pi r cubed. Well, it just told me something important up here. The radius of the sun is about 109 times Earth's radius. So the sun's radius is now 109 times r. Any questions on how I got these two? Okay. So they're asking me to compare. I want to solve for my question. This would just be like an x, right? So what's the rule? X wants to go to the movies by himself. Who's the problem? Earth. So I want to solve for my question, so I need the volume of the sun divided by the volume of the Earth. Okay? Volume of the sun divided by volume of the Earth. So now we just plug in our equations. Except that the volume of the sun for radius, we're now going to put in 109r, and Earth just stays the same. See where these steps go through? Now, what's great about this, what can we go ahead and cancel? What can we automatically cancel here?
4/3 pi.
4/3 pi. I got 4/3 pi on top, 4/3 pi on bottom. Do I even need those? Can I get rid of them? Yes. So should I be plugging these numbers into my calculator on the ACT to try to solve this? No. Worthless. We're going to get rid of it. So really all I have is 109r cubed, or 109r cubed over r cubed. All right? So again, what do I need to plug into my calculator? What rule do I know about an exponent? Raised. What do I need to do? Which rule that we just learned? I've got a 3 on the outside of this parentheses.
That you multiply.
We're going to distribute and multiply it in. Good job. So I would have 109 cubed times r cubed over r cubed. Now, what's my next step? Cancel out the r's. So now the only thing I need is 109 cubed. Okay, so we were able to take something that initially looked super messy with pi and a fraction and all of that, and end up with really the only thing that I need to be plugging in is 109 cubed. All right? Which is 1.295029 times 10 to the 6th. Okay? This is something that we're going to tag along with this chapter. As we get large numbers, like 1,295,029, we can easily write this as 1 with 1 sig big, 1.3 times 10 to the 6th. Okay? So if I put a decimal right here, my 10 to the 6th says I move it 6 places. 1, 2, 3, 4, 5, 6. Who has any experience with scientific notation in your other classes? Iffy? Some? Okay. Then we will go. I'll make sure to hit that. This expects you to have knowledge of that, so we'll kind of review a little bit more on that, okay? So here again, how do we now use what we just learned with exponents to help us when we have really large numbers? Okay, so in this case, we've got big populations, big numbers. GDP means gross domestic product. So we're looking at per capita. Again, this is helping us read through word problems that we're going to see when it comes to SAT, ACT, things like that, and they're asking you to break down what a word problem means. Anytime we see the word per is going to be a fraction. Okay? Capita means person. So I'm looking at price per person. Okay, so I've got a fraction now, money on the top, people on the bottom, okay? So it tells me that my people is 5 million something, which I've rewritten in scientific notation, and I've got my money is million, billion, trillion, whatever that is, out there. So now I've got money, which I've rewritten, okay? Let's do a quick scientific notation. When we have scientific notation, it always has to be a number between 1 and 9, a period, and other numbers, okay? Your first number must be a real number between 1 and 9. You cannot have it in scientific notation like this with a 0 up here, okay? You cannot have scientific notation with 14, with a 2-digit number in front. It always has to be a single number between 1 and 9, okay? Again, scientific notation is an instruction sheet, just like our roots were an instruction sheet. It tells us how many extra zeros we need to have. Zeros move decimal places, right? Because this is tens, or we'd have tens, 100s, or ones, tens, hundreds, thousands. The only thing that's the difference is how many zeros they have. So zeros always move decimal places when it comes to math. So this tells me I need 6 zeros to be moved. Every teacher has a different way to teach scientific notation. Some say if it's positive, you always move it to the left. Some say if it's positive, move it to the right. It really is just kind of a logic game that I kind of leave it up. For me, if my scientific notation is already laid out with my multiplication and I have a positive number, it tells me, for me, I think positive, my number line is moved positive to the right. I'm going to take what I have and I'm going to move it positive. The thing that gets confusing is when you have like this, and you're asking to write it. Well, I know my decimal has to be right here, so I'm going to have 3.45. So in this case, they would often say your decimal is here, and you're moving it to the left, and then you're going to write a positive number. The way I always write it is I write my decimal part first, and then I ask myself, how do I get here? How do I get back? So if I start with 3.45, how do I get back to this big number? I would get back by going 1, 2, 3, 4, 5, 6, 7, 8 positive to get back. So again, it's just a question. Some people will say you put your decimal in, and if you move to the left, if you're moving your decimal from the back to the front, then that's positive. If you're moving it from the front to the back, it's negative. That way has always confused me. But again, everyone has a different way of looking at it. So once we get these big numbers, regardless of how we get them, we get to use our exponent rules for it. Okay, so if I had money put my money one on top and my people one on the bottom, we get to break them up. All I have to do is divide this real part here, and I got 0.249, and then my tens are exponents, so we can use our exponent rule. What do we do if we've got 10 to the 11 over 10 to the 6? 11 minus 6. Excellent. 11 minus 6 gives me 5. So now I have this little digit, 0.249 times 10 to the 5th. See, I didn't actually have to multiply out the whole thing. I didn't have to put those big numbers. Sometimes your calculators don't even allow you enough space for all that. All we had to do was do the real number part. We subtracted to find our exponent part. And we got 0.249 times 10 to the 5th. Now, this is a problem because I have a 0. Okay, so what does it really tell me it is? 24,900. Okay, if we had 0.249 times 10 to the 5th, I can't have my decimal there. It has to be 2.49. Okay, so how do I get from here back to there? I would go -1. So that means I'm going to subtract 1 here. Because to get back to this number, there I went to the negative space. Okay, so if you left it like that, it would be here. We could also see, in this case, we'd go 1, 2, 3, 4. So that's accurate across there. So this is the big picture of how our exponents actually help us. Okay? Everybody stand up.
I have a question about
Yes, sir.
So if you have like say you had 2.409, would you still write 2.409?
Yes.
Or, okay.
So you can't stop writing until you end up with your last number.
Okay, so until you can only.
So even if there's a whole lot of zeros in between and then there's another number, you have to write down to the number unless they tell you significant figures. And that's basically saying write your number out to 2 decimal places.
Like just round.
Yeah, round. Or they might say write it with 3 sig figs. So that means you're going to have 3 numbers after your decimal place.
Okay.
If they don't tell you significant figures, then you have to use all of the numbers that you have.
Okay.
On it. Okay, everyone stand up, stretch. Okay. I have a cord here. I'm actually going to have, I'm going to use this. You guys can walk up here. Let's move some. Let me see where I'm going. Okay. We are going to move up into other polynomials. You guys can move. Come on up here. Okay. No one's moving. Okay. So we knew about linear. We knew about quadratics. Now, if we move up and we have 3 as our highest exponent, that's called a cubic. Why do you think it's called cubic?
3-dimensional.
Because it's a cube. It's 3. We've got a length, width, and height, right? If we move up to 4, it's called a quartic. Okay? So again, these are both standard forms of both a cubic and a quartic one. So if you notice, we start with the highest exponent and we move our way down. Okay? If an exponent is missing and you have to write it all out, what number would you put there? In this, if this was missing and I said you need to write out all of the parts of the standard, what number do you think I would put here? It's addition, subtraction. What? 0, because 0 doesn't change anything, right? Okay, so when we had quadratics, and we had our lines, and they started bending, okay? So we have our nice little parabola here. We were able to look at it and go, oh, well, that number that was at the very beginning gave me a lot of information. Okay, so in the same way, this one, we are going to look at it and we are going, okay, I'm going to skip because I want to explain and then we're going to go back. Okay, that number has a lot to tell us, okay? So just like when we had a line, okay, we knew that that number in the front told us where it was headed, right? Either it's positive or it was headed negative. When we had our quadratics, it told us if it faced up, if it was positive, or if it was negative, okay? You will start to see in your book and information, they're going to start using the infinity sign. It says laid down 8, either positive or negative, and they write the formulas with like f of x with all these infinity signs. You're like, what the heck are they talking about? It's even confusing for me whenever I was looking at it, so I'm not going to explain it the way that the book explained it. Right? What we're going to learn to do is that we're going to look at it in our real life. If I have this parabola, as my line moves towards positive x's, my graph is going towards what? Positive y's or negative y's? Positive y's. So it could be written as f of x, which is another name for y. Good job. As y goes to positive infinity, meaning it's going positive, then x is going to positive infinity, right? It could also be said that as x is going towards negative infinity, all of my x values are going more and more negative. My y values are doing what?
Still positive.
They're going positive. So as x is going to negative infinity, it's also going, y is going to positive infinity. Okay? So we could evaluate the same thing here. My x's are going positive, but my y's are going negative. My x's are going negative, and my y's are also going negative. Okay? So where our line is going, we get to start having information about that. Okay? So in the they write it like this. Doesn't that look nice and confusing? Yeah. So all you need to know is this part. It says in real words. In real words, what they are saying. Let's think about this one. What would be the coefficient on this if I were to write this out? Someone give me an equation for that graph. Oh, it's at the vertex, so and maybe it's, so we'll do 0, maybe it's at like 0, -1. Okay. What could be the coefficient there of this graph?
Something negative.
Something negative. Say, and it's pretty wide, so maybe like -1/2. Right? Would that be valid? It's wider than our regular one, so it needs to be a fractional number. It's negative because it faces down. Okay? So, my little coefficient value there tells me where it's headed. Okay? So, all of this says is that if our coefficient is even as we start getting bigger, then our graphs are going to go in the same direction. If our coefficient is, if it's even, then they're going to be facing up, positive, just like regular. If it's odd, they're going to be facing negative. Has that changed from linear to quadratic to anything else? No. Okay, so this is the other thing I want to show you. I need help moving this into a different shape, and you guys need to see it. Okay, so here I have a parabola. It's both facing what from you guys' direction?
Positive.
Positive. Okay. If I change this to a cubic, it is going to look like this. Okay, see that? So now I have one side that goes up and one side that goes down. Okay? If it's quartic, it's going to be back like this. what way are they both going? Okay? If it's to the 5th, it's going to look like that. What way are they both going? Opposites. If it's to the 6th, does anyone see a pattern?
No.
Are they going the same? If it's to the 7th, it's going to look like that. Okay? What pattern do you think there is? So when they're even, they face what?
Same direction.
The same direction. When they're odd, they do what?
Direction.
Opposite. And look, how convenient. Doesn't it look like odd turned upside down? Opposite. That's real convenient. God did that for us. Odd is opposite. So if it's even, and even has 4 letters, and same has 4 letters, there's lots of little things. Okay, you guys can sit down if you want to get back in your seats. Just want to get you some mood. So, as we start moving through these quadratics, and we're looking at our different graphs, I'm going to pull up. I should have already had that. Desmos.
Are we gonna have to graph those functions like quartic and?
I don't know. Haven't decided. Wait, it's not letting me say it. Okay, I'm not gonna do that right now. I'll just post it for you guys later. Okay, so the important thing to know about this, as we have our equations, and I have a whole bunch of examples to look at. If I have okay, and I have a number. Okay. And then it has a whole bunch of parts after it. Okay, so now we have our equation. And it starts y equals 3x cubed. Okay? My first number tells me the same thing it has told me all along. It tells me the direction that we're going. Okay? So if it is a positive 3, my graph reading from left to right is going to end positively. Okay? So if I have a graph somewhere, I'm ending positive, right? Then we move to our exponent. Our exponent tells us about the other end of the graph. If it's odd, what did we decide? Odd equals
Opposite.
That's it? Okay. So if my graph ends positive, just like, you know, if I had a positive parabola, okay, so my graph ends positive, but I have a 3 up here. That means it starts the other direction. And then it does something like that in the middle. Okay? So if I'm looking and comparing graphs, I would need to find one that ends positive and faces different directions. Correct? If they're asking you to match, are you actually finding other solutions? Is this just a real good shortcut? Figure out what you're at? Yeah. So let's think, what would the second one be?
Starts negative and in the same direction.
So, no, so we're looking at end. It's always end in behavior. So I've got -2. So it's going to end, and we're looking at y values, so it's going to end going negative. Okay? But I have a 4. So where does it start? Facing the same direction. They're going to be going in the same direction. So it's also the two ends have to be the same direction. So this is opposite direction, same direction. Okay? And our coefficient tells us the way it faces. We're actually dealing with the end behavior of it. Okay? So let's look at this one. 4x to the 12th. How would I graph the end of that one? 4 tells me it goes where?
Ends positive.
It ends positive, so I'm going positive. My 12 tells me
They start the same direction.
they're the same direction, so this side of the graph would also be going up. And it's going to do something like that in the middle. Okay?
Why would it be like that?
I'm going to talk to you about that in just a minute. Right now we're just going to keep knocking this one out, okay? So now for this last one, negative 6x to the 15th. Where am I ending?
Ending in a negative.
Ending negative. Okay? What would the other side, where is it coming from?
Coming from a negative.
15 is even or odd? Odd. So if this one's ending negative, it's got to be coming from up there. They've got to be in opposite directions. Okay? I have... forgot about my paper. Okay? I'm going to pass out these papers. We're going to look through this. We're going to look through these. It has a little solution paper. Right on it too. Okay. Did you get a solution paper? There you go. Okay, so on the first one, all we're doing is identifying where it's at. The first one, where is it ending? Where's this left side of the graph ending? Positive. That's not a marker. Okay, so it ends positive, and the coefficient must be what?
Even.
Even. So it's positive and even. Excellent. There's your candy. Pick one. Okay? Isaac, next one. What would it look like? It's going to end what? It ends positive.
Start up down.
So are they going to be the same direction or opposite direction? Opposites. So because it's odd, so they're going to be opposite directions. So I think on there you got, what are they asking?
2x, 30.
Even. So that's going to be, it is positive and odd. So then you would just circle the 2. Falls under positive and odd. Right? Okay? You don't have to do the worksheet with it, okay? We'll do number 3. What would the coefficient be?
Negative.
Negative. And then the exponent would be
2, so
even. And it would be 2 in that case. So we're looking at the coefficients, we're looking at the exponents. Okay, Jace? It says the leading coefficient is -4 and the degree is 7. So it's going to be what? Negative, so it face negative. And it's going odd, so it would look like the one that we have up on the board. Okay? Perfect. Ella, do number 6. Pick it. How does that number 6 end?
Positive.
It ends positive. Okay? So the first coefficient would be positive, right? The n's positive. And what would that coefficient be?
Negative.
The coefficient's not negative, it's either
Odd.
odd. It would be odd. Excellent. Okay, Anna, look at number 7. Number 7, our leading coefficient is what? Positive, because it's positive 2. And will they go the same direction or opposite directions? The same, because the exponent is 6, right? Pick something. Okay, Tessa, number 9. What would that coefficient be?
Positive and odd.
Positive and number 9. Positive and even. So the coefficient would have to be positive. The exponent would have to be even. Right? And Aaron, look at number 11. What would it have to be? The first coefficient would have to be what for number 11? Where does it end?
Negative.
It ends negative. And the coefficient would have to be odd. Perfect. Okay, so do we see how we can look at a graph, and now we can look at our equations, and we can figure out what our graph should look like? So where do we go from, what else does it tell us? Well, while you won't always see all of the solutions, let's think about it. When we had a linear equation, when we had an x to a coefficient of 1, and I wanted to find a point where it crossed the x-axis, how many times could that line cross the x-axis? Any line, how many times can it cross the x-axis? Once. And my coefficient was what? 1. When I had a quadratic, how many times could it cross the x-axis? Because it's a parabola. So for my linear, I could have 1 solution. For my quadratics, I could have 2 solutions. How many times do you think a cubic can cross the x-axis? 3. It is a graph that looks like this. 1, 2, 3. At most, it will have 3 solutions. If I have a quartic, at most, it could have 4 solutions. Okay? So our exponent not only tells us what our end behavior is doing, it also gives us that extra clue of at most. It doesn't mean it will. It just means the most amount of solutions that it could have would be 4. So if I was given a graph that looked like this, what would my exponent have to be? If it crosses my graph, if it crosses the x-axis 6 times, that means the smallest coefficient would have to, or the smallest exponent would have to be 6. It could be greater than that, because you don't always have to have all the solutions. Parts of it could be, the movement could be above or below the x-axis. But it would have to, excuse me, at least be the exponent of 6. Do we see how our exponents also tell us how many solutions that we can have? Okay. Okay. So now that we can read a graph and we can read these larger polynomials, we have a couple of minutes to go back.
Do you think you could go through 5 and 12, like those kinds of problems? It's like as x.
Yes, so let's think about it. Perfect, thank you for asking. Okay, number 5. Let's see what it's saying. As x goes to positive infinity. So that means I'm looking at my values that are, my x values are going to positive infinity. My y values are going negative. So for every point, as x gets bigger and bigger, my y values are going negative. Okay? So for the other one, it says as x goes to negative infinity, so I'm thinking I'm getting negative x values. My y values are doing what? What does it say?
Going negative.
My y values are, so if I go x negative, my y goes negative. If I go negative again, I go more negative. Okay?
So that one would be even and negative then?
So the coefficient would have to be negative,
Right.
right? It might be negative x to the something. What would my exponent have to be? An even number. So this could be negative x to the fourth.
Okay.
It would have to be even because they're going the same direction. My coefficient has to be negative because they're pointing down. Okay? So then let's look at 12. 12 says, while x is going positive, y is doing what?
Going negative.
Going negative. Sorry, I would catch. Okay, and then it says, as x is going negative, y is going
Positive.
positive. So my coefficient has to be what?
Negative.
My exponent has to be what?
Odd.
Odd. Could be 3, 5, 7. Anything else?
Makes sense.
Does that make sense?
Yeah.
Any other questions on those?
You said we're not turning these in, right?
No.
Okay.
Okay. So, one of the things that we'll need to go over, and I'll make sure and take this, we won't have homework on these. Okay. Is how do we start working out I gotta back myself up. Okay. How did we get there in the first place? Okay. So a couple of things. I was totally going the wrong way. No wonder it wasn't making sense. Okay. So what makes a polynomial function in the first place? One, every base has to have a real number exponent. So if you have an exponent that's a variable, it's not a function, right? You also cannot have negative exponents. So if you're going to have it as a function, meaning it's going to pass that vertical line test, everything has to be a positive exponent and has to be a real exponent. Okay, so that's just simply to know that. So we solve it the same way that we would solve any other function. If I had f of x and I have something and I choose to say 3, this is the instruction sheet that tells me everywhere I see my variable, I'm going to plug in a number. And we would end up solving across. Okay, as we get into larger equations, this can get real complicated, right? We've got a whole lot of numbers we got to deal with. What if we started with the exponent of 7? We would have 8 terms, lots of multiplication that we would have to deal with. Okay? So a way that we can do this easier is with something called synthetic substitution. And we also will divide next week with synthetic division. So I want to give you a heads up on this one for this week first. So then that way next week it makes it a lot easier. Okay, so if I were to actually plug in that FF3 like I just did here, and I know I ended up with 162 minus 72, 15, and negative 7, okay, across. If we have, I don't really know if that was the same problem. Yeah. If I was to actually plug them all in, I ended up with a solution of 98, right? Well, with synthetic substitution, what we do is we get rid of all of the variables and we're only gonna deal with the coefficients. So in this case, we started with a 4. Where is our x cubed?
Gone.
We don't have one. So as Isaac said, we put the number 0. So if I were going to have a thing, I would basically say, here's my to the 4th, x cubed, x squared, x, and then my constant. Okay, so this is the coefficient to the 4th, coefficient to the 3rd, coefficient squared, coefficient 1, and then my constant. Okay, we drop the coefficients down and we start at the beginning, and all we're going to do is drop and multiply. Drop, multiply, add, and we just kind of zigzag our way back. So this 2 drops down. I'm using the number that I had for 3. I'm going to do 3 times 2 is 6. Now I add these two together and I start it over again. 0 plus 6 is 6. Now I get 3 times 6 is 18. I'm going to add these two together. Negative 8 plus 18 is 10. Do it again. 3 times 10, 30. Add them together. 35. 3 times 35, 105. 105 plus 7 gives me 98. Did we get the same answer? Cross there. Okay. So that's synthetic substitution. We will go over it more next week, but just so that you've had your eyes on that, we'll start there next week and move on. Right? So you guys have your test this week, and then I'll just give you some homework that is identifying end behaviors of those functions so that we can get used to evaluating those equations again. All right? Sound good? All right. Elise. We spent extra time at the beginning for the review, but I think it's important since you guys have a big test this week. If you have any questions, please contact me before the test. I will gladly help, explain, whatever. Email, text, FaceTime, Zoom, whatever you need.